saturated. Today, we are going to look at soaps and detergents. Soaps and detergents. One of the chemical properties of fats and oils, of course, that we discussed in our last class was saponification, which we said is the alkaline hydrolysis of fats and oil to produce soaps and glycerol. Okay, alkaline hydrolysis of fats and oil to produce soaps and glycerol. So we are going to link that to what we'll be discussing today, which is soaps and detergents themselves. And we're going to look at the objectives of this class. Okay, so by the end of this class, you should be able to define saponification, describe the cleansing action of soap or the emulsifying action of soap. Then you should be able to distinguish between soaps and detergents. And of course, you should be able to make a simple soap, all right? A simple soap. So let's look at what is soap. What is soap? Kenechukwu, can you read what's on your screen? What you can see there? Okay, for Kenechukwu.
Soap can be defined as the sodium or potassium salts or fatty acid.
Very good. The sodium or potassium salts or fatty acids. In our last class, we looked at some fatty acids. We looked at palmitic acid. We looked at oleic acid. So, and you know that these acids have an ionizable hydrogen. Every acid has an ionizable hydrogen, right? Now, when this ionizable hydrogen is replaced by sodium or potassium or any metal, we say that a salt has been formed. Now, specifically for soap, when the long chain fatty acid molecule, when the hydrogen on the long chain fatty acid is replaced by sodium or potassium, we say soap, of course, which is the salt of the fatty acid, has been made. Are we together? Just a minute. Hello, class. Just a minute. Can you hear me? Just a minute. There's something I'm supposed to set up that I didn't. So I want to do it real quick. And I'm not able to do it here. So I'm going to leave the room briefly and come back right in, okay? Okay, sorry, I'm back. Sorry, I needed to set up something in the other class. Sorry, so let me share back my screen again. Um, okay, soap can be defined as the sodium salt of fatty acids. So, soap is manufactured by heating natural fats and oil of either plants or animals with a strong alkali. Now, this type of reaction is called what? This type of reaction is called root. What do we call that type of reaction? Root, can you hear me?
I
Hello,
don't have an
Ruth.
idea, sir.
No. Yeah. Okay. Okay. I mentioned it like twice today or three times. Ugoma, what do we call that reaction?
Saponification.
Saponification. Very good. Okay. That change is called saponification. And as we can see right here, we'll see that the fat molecule is reacting with 3 moles of sodium hydroxide to produce glycerol and soap molecules. So for the sake of emphasis for this class, I want us to, again, once more remember, I want us to remember that this R is a long hydrocarbon chain. This is very important for what we'll be discussing today. That R there is a long hydrocarbon chain. Are we together? So this saponification process produces soap and it produces glycerol as well. Now, let's look at the manufacture of soap. Let's look at the manufacturing process of soap. Palm oil or granite oil or any of these triglycerides is steam heated in a large pot with either sodium or potassium hydroxide solution mixed in it. This will be stirred continuously until it traces. To trace means it will become like pap. It will become like custard, like you're making custard. Okay? And we'll continue stirring. When it traces, we'll say saponification has occurred. Then this soup is now poured into a mold. But before you do that pouring into a mold, concentrated sodium chloride is added, stirred and allowed to cool. You need to understand what role concentrated sodium chloride is playing there. This concentrated sodium chloride will actually cause the soup to separate from the mixture. It reduces the solubility of soap in glycerol. So you now have the soap batch floating on the glycerol under. The glycerol will be under, the soap would be at the top. This is called salting out. Take note. This is called salting out. And why is it done? To decrease the solubility of the soap. So basically, let's run through the steps again. Palm oil or your triglyceride or your fat or oil is steam heated in a large pot with either sodium hydroxide or potassium hydroxide. This is stirred continuously until saponification is completed. Now, concentrated sodium chloride is added, stirred, and allowed to cool. And I told you what this concentrated sodium chloride does. It separates the soap from the glycerol. You have the top batch, which is the soap, then under it, you have the glycerol. This is called salting out, and it is done to decrease the solubility of the soap. Now, we are going to look at the soap structure. Pay attention to the soap structure and understand it very, very well. The soap you use at home, even the detergent you use at home, we are going to look at their structure now. It is their structure that will help you understand their cleansing behavior, how they do their cleansing. We are going to look at the detailed cleansing behavior of soap. So I'm going to draw the structure of soap molecule. Remember, it's a carboxylic acid, therefore it will have the head CO. Sorry, it's from carboxylic acid rather. So it will have Na. But remember, it is ionic. The head is ionic. So the Na is plus, the COO is minus. Then back here, we now have the hydrocarbon tail. Now, this hydrocarbon tail will now depend on which fat or which oil it came from, but that is not what is important. The most important thing here is that it has a head which is ionic. So let's write it there. Ionic head is very important. You draw this. It has an ionic head and it has a hydrocarbon tail. A hydrocarbon tail. Hydrocarbon tail. Are we together? So these two features of the soap is very, very important that you understand, because it will help us understand, like I say, how soap does its cleansing work. So this ionic head, remember, like dissolve like, isn't it? That means ionic compounds will dissolve in ionic solvent, or polar rather, polar compounds will dissolve in polar solvents. It's not appropriate to say ionic compounds in ionic solvent because water is not necessarily ionic, but it is polar. So we say polar compounds will dissolve in polar solvents. Now, because the head is polar, now, for the sake of those who do not know what we mean by polar, when we say something is polar, it simply means that it has charged ends. It has positive and negative ends. So anything that has positive and negative ends is polar. All right. So you can see here that the head is polar. So we say it is hydrophobic. Sorry, hydrophilic rather. Hydrophilic head. And what we mean by hydrophilic head, again, is that it is water loving, hydro, water, philic, loving, or attracted to. Are we together? So the head is hydrophilic because the head is polar, just like water is polar. All right? But the tail is hydrophobic. Now, who can unmute and tell me what hydrophobic means? Yes? Who can tell me what hydrophobic means? Nobody? Kenechku Okafo? Okafo Kenechku, what does hydrophobic mean?
Well, phobic is fear,
Okay, phobic means fear or
then
withdrawal from.
hydro from
Okay,
something.
hydro is what?
Okay, then hydro. Hydro should be like water house. I don't
Water.
know.
That was what I said
Around
initially for hydrophilic. Hydro means water in this case. Phobic means fear or dislike. Exactly. So when we say the tail is hydrophobic, we say the tail is not water loving. The tail is it does not blend with water. The tail does not dissolve in water. Are we together? Are we together there? I hope everybody understands this. Okay? The tail does not like water, but the head likes water. The tail actually loves oil. Okay, this is a covalent hydrocarbon molecule, so it will be soluble in grease and oil, but the head is not soluble in grease and oil. Are we together? Now, this structure makes it soluble in both water.
I knew it. His internet is bad, guy. Please now, that check that, please. Please now, that check that thing I told you to check. And this part I've been on since. I've not been on no. They took white. Emergency doesn't come go to mechanic.
Hello, hello,
So that means you
hello.
know.
Yourself.
Okay.
Mute yourself. Thank you. Okay, so I said this structure makes it soluble in both water and grease. In both water and grease. I hope everybody can hear me. Can you all hear me? Please, if you can hear me, unmute
Yes,
yourself.
yes, yes, you can.
Oh, great. Okay. Okay, I just want to be sure.
Yes,
Okay,
sir.
now we have a hydrophobic tail and a hydrophilic head. So when it wants to dissolve in water, it will dissolve with its head. But when it will dissolve in grease or oil or non-polar liquid, it will dissolve with its tail. This dual feature, this dual ability is actually capitalized when soap does its cleansing activity, like we are going to see shortly. Okay, so let's quickly look at the cleansing action. Let's quickly look at the cleansing action of soap. Kenechukwu, can you please read what's on your screen?
When a soap is put into water, which has a greasy cloth in it, the hydrophobic hydrocarbon chain on each soap molecule dissolves in the grease and becomes embedded in it.
And becomes embedded in it. Very good. Now, this agrees with what I was saying earlier, isn't it? That the tail will dissolve in grease or oil. The tail will dissolve in grease or oil. Now, Ruth, I want you to read the next sentence.
On the other hand, the hydrophilic ionic head group is strongly attached to the water molecules.
Very good. So one is attracted to water molecule and the other is attracted to the grease. Okay? It's attracted to the grease. And what do we get? Fami Roju, is your network sharp today? Emmanuel, can you read what's on your screen?
When the water is stirred, the grease is slowly released and is completely surrounded by the soap molecule. The grease on agitation breaks into smaller pieces, each surrounded by the soap molecule.
Okay. I think I got that. That's very good. Now let me explain what you are looking at there. Let me explain that. Now, let's say this is your fabric. Let's say this is your fabric. So let me use black there. Say this is your fabric, okay? And this your fabric has a grease stain on it. So let's make this brown color our grease stain. Okay, this is a super magnified diagram there. So this is our grease stain on the fabric. All right, this fabric is already inside water. Okay, it's already inside water. So what actually happens is that the soap molecules will keep their head in water. They'll keep their head in water, then put their tail inside the oil. Head in water, tail in grease, head in water, tail in grease. So this is what happens. So when you soak your fabric before you wash, this is the alignment taking place. Okay? So let's put all those molecules there. All the molecules would bury their tails in the grease and keep their head in the water. So let's assume the white part of the screen is the water, but the brown part is the grease, and the green here, in this case, the green snake-like structures are the soap molecules. Let me add one more there. Yeah, there. Good. So this is what happens during soaking. The entire surface of the grease is covered with soap molecules, all burying their tails inside the soap molecules. But there's something I need you to remember about the soap. There is something I need you to remember. Take
Line
note.
breaking.
Am I breaking? Sorry, am I breaking?
Yes, it's breaking.
Oh, that's bad. And I'm very close to my head. Let me change. Let me see if I can switch my network. Oh, there's no light. I don't know. Am I sounding better? I just hope I'm sounding better. Okay. Somehow we are going to get a recording of this class, so I think it's still going to sound better when we get a record, even though I still need you to understand this very clearly. All right. I think the network, I don't know, for whatever reason, the network is very poor this evening. I don't know why. Okay. So here we have these heads, but I said there is something about the soap molecule that I want us to remember, that the soap molecule is like this, and the head is COONA. Okay, the Na is plus and this is minus. Now, when this soap molecule is dissolved in water, remember, because the head is ionic, the sodium will disappear, and this is what will be left of the head. The COO minus is what will be left of the head because the sodium would be free to move about as an ion in the water. I hope that is clear. If that is clear, what that means now is that all these heads are negatively charged. So let me put that there. All these heads, are negatively charged. So let's put their charges up there. All the heads are negatively charged. On agitation, when you now agitate, when you start rubbing and scrubbing the fabric by way of washing now, these soap molecules will yank up the grease from the surface of the fabric. They'll break the fabric into smaller pieces, you understand? Then each grease piece, so let me draw a grease piece here. Each grease piece like this will be surrounded by soap molecules. So let's have our grease piece like this. So assuming this is a small piece of grease, this small piece of grease is going to have soap molecules surrounding it like this. Please pay attention to this because you should be able to describe this when you are asked in an exam. You should be able to describe this. Okay? Now, this thing you are looking at here is what we call micelle. Okay? It is called micelle. If you want the spelling of micelle, that's it on the board there. These are called micelles. So let me draw yet another one. Let me draw another one. You should have this diagram in your notebook. So this is another grease particle. Then These are soap molecules surrounding it. So on agitation, you're going to have plenty particles of this. So on agitation, you're going to have plenty of these, each surrounded by soap molecules. But remember that these soap heads are negatively charged. Each of these soap heads are negatively charged. What that means is that this micelle will be like a negatively charged ball. So I want to ask a very simple question here. Ugoma, mute
Yes,
yourself. Good. Ugoma, what do you think is going to happen when these micelles come together? When these micelles try to come together, what will happen?
he carries the grease away
No, I mean when this one comes this way and this one comes this way for them to meet, what will happen? Can the
oh
grease come together?
um no,
Why do you think the grease cannot come together? The grease pieces, why do you think they can't come back together?
because they are they are of the same charge.
Beautiful, beautiful, excellent, excellent, very good. Because they are like charges, those negative charges around them will keep them separated, will keep them apart. All right, it will keep them apart. Now, if you're at home, maybe after this class, you may want to try it out. Okay, if you put a small amount of water inside a PET bottle, maybe a water bottle, all right, you put small water into it, maybe a quarter the volume, put water into it, add oil to it, and shake vigorously. Shake with all your might, all your energy. Shake, 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 shake. When you shake vigorously, you notice that the oil will scatter inside the water. If you're able to agitate very, very well, you notice that the oil droplets will scatter inside the water. When you have oil dispersed inside water like that, with tiny, tiny particles of oil, it will look like it's dissolving inside water. When you get something like that, we say that emulsification has taken place. Emulsification has taken place. But unfortunately, that kind of emulsification will not last. Why wouldn't it last? If you keep the oil and water mixture after the agitation, if you just keep it, all the oil droplets will do what? They will come back together. And within minutes, the oil will float on top of water again. You now have the oil layer on top of the water layer. But if you add a small piece of soap, if you collect soap, okay, and you throw into the mixture and you now shake again, you now agitate. If you shake very well, you might come to a point where the whole mixture will become cloudy, like milky. In fact, if you are using palm oil, it will turn yellow. Now, what is that milky or yellow color you are seeing? What actually happens there is that each of the droplets of oil will be surrounded by soap molecules like this. Each of them will be surrounded by soap molecules. And when they are surrounded by soap molecules, it means that if you keep them like you kept the first time, maybe after 10, 20 minutes, you see that the oil will not come back together. And the reason why it will not come back together is because the head of the soap molecules are all negatively charged. And like charges do what? Like charges repel. Like charges repel. They do not attract. Like charges repel. Are we together? So that is the case with this. So these micelles, we keep the grease molecules separated and it will be easy to rinse off. It will be easy to rinse off. And that way, the grease is off the fabric or the plate. as the case may be, depending on what you are washing. I hope this is clear. So I want anybody that has a question now, I want to pause here. I want to entertain your questions here now. So if you have a question, please feel free to ask now.
So I just want a bit clarification on something.
Okay, go on.
You were using the example of our clothes being inside water and stained with grease.
Yes,
Now,
yes.
when the soap is being applied on it,
Yeah,
the molecules of the head will stay in the water and then the tail dissolves
in
inside the
degrees.
grease.
That's right.
Now, how will you explain if after the washing, then some
Uh-huh.
part of the grease still remains on the clothes?
Oh,
Will
very
you
good.
say that it's not enough soap applied?
Very good.
On
Very good. Usually, it depends on the thickness of the grease. Okay? The thickness of the grease. All right. And remember that the soap, that is why soaking is important. The soap will need to actually bury enough molecules in the grease. So, yes, just like you rightly said, you probably do not have enough soap to remove all the grease. So what probably has happened is that the soap molecules on the surface have removed some layers of the grease, but there are still some grease there and you have rinsed. You understand? And you have rinsed. But if you see the grease, you understand? If you see the grease stain, let's even say it is palm oil, for instance. If you see the grease stain and you rub more soap on it and you agitate a little more, you notice that more grease will leave. So
Come on.
yes, if you do not have enough molecules of soap, you may not be able to wash off the grease very well. Even on your hand, if you do what will I say, if you do something that has to do with oil and your hand is oily, for instance, and you now want to wash it and you can only find a very small piece of soap, you see that that small piece can only do a little. It will wash off something, but it will wash off everything, isn't it? But if you
Yes.
have enough, and the ladder is rich, if the ladder is rich, that means you have enough soup. Then of course it is going to remove the entire grease eventually. Sometimes you just need to agitate some more so that the soap molecules will reach deeper levels, deeper layers of the grease or oil stain. All right.
Thank you, sir.
You're welcome. Thank you for asking, Ruth. So any other question?
So this when the water is stirred and the grease is under what?
Eh?
This when the water is stirred, all these things that they wrote
We are
is
talking
under.
about cleansing action of soup.
Okay.
It's still under the cleansing action of soup. You may even pair it up with emulsifying action of soap. And the reason is because soap it cleans grease stains by emulsifying the grease. So the cleansing action of soap can be the same as emulsifying action of soap, even though in some textbooks you see them treated separately. But if they give you the principle in both of them, you see that it's the same thing they are talking about in both cases. So it is the cleansing action of soap or emulsifying action of soap.
Okay.
Thank you for asking, Kenechku. Anybody else? Anybody else?
And what's this first thing that you drew? That is like line.
Which one? The black one?
Yes, the black line.
That's the surface, that's the fabric surface. That's the fabric. Okay, so let's label them. Let's label them. Thank you for bringing my attention to it now. So this is the fabric. Fabric. This brown one is the grease. Let's call it grease stain. Okay, then these green gentlemen that are lined up are the soup molecules. Soup molecules. Okay, so when they break off from the fabric and they form these ones we call micelles. Okay, those are micelles. So let me repair the diagram of my micelle so that you don't add arrow to the micelle. So those are micelles. And I hope that is clear.
Yes, it's clear.
Good, good. Any other question? No other question? Ugoma, no question. Before you answer, think very
No,
well. Oh. Think very well because I'm going to ask you to describe this same thing I described. Emmanuel, no question. Emmanuel, are you still with us? No question?
Then wait, sir. When the grease breaks into smaller pieces,
Yes.
what now happens to the grease? It now washes off.
It's surrounded by soap molecules to form the micelles. And because they can't come back together to form the large mass of the grease again, they are so tiny so they can easily be rinsed off.
And stuff. Okay.
They can easily be rinsed off. So you may even try it with a plate if you go to the kitchen. I know you don't know how to cook anything, but you may
I
you
can
may
cook.
just oh, it's a lie. It's only hot water you
I'm
can boil.
serious. I
You can
can
only
cook.
boil hot water. So you may go into the kitchen, you know, just deliberately smear small palm oil on a white dish, white plate. Okay, it's easier, it's more obvious on a white plate. Okay, just smear the oil on it, rub your hand on it. Okay, then collect not detergent. Soap will do the same thing. It's the same thing soap does that detergent will do. Okay, the only difference between soap and detergent we're also going to see here. Okay, so just collect soap, put in water, you know, just make a small, will I say paste, not necessarily paste. Just put soap in water so that a reasonable amount of the soap will dissolve in the water. Then drop it or pour it on the oil. Then rub your hand on it. You see that reddish oil will start turning yellow and it will be moving easier on the plate. Like if you pour water on it, if you pour water on the oil before you put the soap solution, the oil will just be there looking at you. But if you put the soap solution, rub it on the oil gently, just rub it to mix very well with the oil. If you pour water on it, you see it washing off. Now it is washing off because it has formed so much micelles, very tiny, tiny, and they can't come back together. That's the winning point there. They cannot come back together. The oil droplets want to come back together to coalesce and form larger uh, oil body, isn't it? But because these heads are all negative, it keeps each piece apart. And now it makes it easier to wash them away. Okay?
Okay.
Good. So I want to assume that this is clear to everyone and we can forge ahead from here. So let's look at detergents. Let's look at detergents. One of the things you heard when you did water, types of water, you know, hard water and soft water, isn't it? And we are told that hard water wastes soup. Hard water wastes soup. Now we are going to have a better understanding of how the hard water wastes soup. We are going to look at the chemistry. That means we will mentally go into the water, the soap solution, and see how calcium and magnesium will cause the soup to form scum instead of doing some cleansing action. So in hard water areas, an insoluble scum forms when soap is used. Now pay attention. I'm going to illustrate this and I need you to understand it very well. This is your water surface, okay? And inside this water surface, you have calcium ions and you also have magnesium ions. Are you with me? Now, remember that the soap molecules, I told you, when the soap molecules come into the solution, come into water, they come as what? Let's go back to our green. It comes as Na, there is COO, then there is the snake part. Then there is Na, there is COO, then the zigzag hydrocarbon part. Now pay close attention. I need you to get this. When this dissolves in water, the Na moves on its own. That's goes away. Okay, it's dissolved now, so it is now free to move wherever it wants to go to. And this one too will move to wherever it wants to go to. All right. So the head, what is remaining of the head is the COO minus. Please stay with me. Is the COO minus. Now, the cleansing action is supposed to be done by this molecule. Remember? It's supposed to be done by these molecules. Now, this is where the problem now comes. These molecules come into water and they come in contact with calcium and magnesium. Let me bring it close to calcium. Let me bring it close to calcium. So when it comes close to calcium, it forms OO. This is the COO. Then this is the snake part. Then another COO. Don't mind the size. And another snake part. This is the new molecule it forms. This is now the calcium salt. It came in as sodium salt, but it is ending up as calcium salt. I need you to understand this aspect first. Why am I using these two molecules on one calcium? The valency of calcium is 2, and the valency of the, let's say, stearate now. The valency of the stearate is 1. So you need 2 of the negative molecules to neutralize 1 ion of calcium. Now, remember I said that the soap came in as sodium stearate. For example, assuming we are using stearic acid, the soap will come in as sodium stearate. But when it comes in, sodium will leave the soap and go its way. Then the stearate will now combine with calcium, which is present in hard water. Remember once more that what causes hardness in water is calcium and magnesium ions. So the same thing happens here. This one too will grab its own. Sorry, I'm going out of the water now. I shouldn't go out of the water. And again, OOC, then like that. It also forms its own. This one now is magnesium stearate. And this one now is calcium stearate. The problem with hard water is that this stearate that the calcium forms with this soap molecule is not soluble in water. It does not dissolve in water. Now, stay with me. I want you to understand what that means. That means that there is a marriage between these two that does not allow these molecules, these green molecules now, these soap molecules are not allowed to go and perform any function. They are married and they stick to calcium. And as long as they stick to calcium, they are useless as far as cleansing property is concerned. Before I move on, I want anybody that has a question to please ask. Please ask your questions. I want to be sure you understand this very, very well. Because when they say hard water wastes soap, You need to understand clearly what that means. Go on, Kenechiko, ask your question.
I don't understand.
Okay, you don't understand what I just explained.
Yes.
Hello, I can't hear you.
Yes. Yes.
Okay, I'm going to take it all over again. I'll take it all over again. So let me clear everything on my board. So now I said, this is water. Let's make this the surface of our water. Okay? And inside the water, we have soap molecules. This is the head, and this is the tail. And the heads are negative. Are you with me? We just have so many soap molecules in the water. The heads are negative. But these molecules, instead of doing some cleansing action, instead of going to bury their tails in grease, they interact with calcium. This is calcium, Ca2 plus, to form a new salt that is not soluble in water. Kenechiko, are you there?
Yes, I'm there.
The reason why soap can do some cleansing is because soap is soluble in water. You need to get that one clear first. But when soap comes into water that contains calcium, it forms a new compound that is not soluble in water. And that compound that is insoluble in water is what we call scum. So scum is the other salt that is insoluble in water. So if this is from stearic acid, let's say sodium stearate. Sodium stearate is our soap. Sodium stearate is our soap. Sodium stearate comes into water, ionizes into sodium ion and stearate ion. The stearate ion is now attacked by calcium ions to form calcium stearate. That calcium stearate is what we call scum. This sodium stearate is what we know as soap, is a type of soap. I don't know if this makes sense. And once this scum is formed, the scum itself feels greasy. It will just float on the surface like some grayish, greasy matter on top of the surface. So the soap molecules that are supposed to be burying their tails in grease to help in cleansing are coming out of the water as calcium salts. So they are precipitated, if you understand that. They are precipitated as calcium salts. It's just like sending people to go and do some work. For example, you are all in this class. Let's say we are 20 in this class. And I sent 20 people to go pick logs of wood. Okay, so there is a heaped log of wood logs in a place, and I need you to collect them from there. Just remove them from that space where they are. And when you come in to do the work, instead of you to go pick the wood, everybody a piece or everybody 2 pieces, you meet some friends there and you start gisting. And from gisting, you now escort your friends out of the place. You escort them to their houses. Has anything happened to the log of wood? No. The heap will still remain there. Why? Because you have engaged with something else. And that something else that is now distracting the soap from what it's supposed to do is the calcium. Calcium will now connect with these soap molecules to form an insoluble. That's where the problem is. The problem is not that they connected with calcium. The problem is that when they connect, they come out of water. They precipitate out of water. You understand? They are no more ionized. They are no more present inside the water as ions. They have been removed from the water. They will now go and float on top of the water. This is what we mean by wasting of soap. So, Kenechika, I want you to come back again and let me know if you understand. If you do understand, I might need you to tell me again what you understand.
I understand.
You understand?
Yes.
Are you sure you understand this very well?
Yes, I understand.
Very good. Is there any other person in the class that does not understand?
Uncle, I have a question.
Do ask, please, my dear.
If there's an oil stain, why
Huh?
does detergent remove it better than soap?
Uh-huh. Uh-huh. I have just explained to you why soap has that weakness. Okay? Because soap is calcium stearate. Okay? Now, detergent, the salt that calcium will form with detergent is soluble in water. That means the calcium does not have the capacity to distract the detergent molecule from what it is supposed to do. The detergent molecule will go on with its task without getting distracted by calcium. That means calcium cannot precipitate it. Calcium cannot remove it from water. So the summary of the answer to your question is that the salt formed by soap with calcium is insoluble in water. But that which detergent forms with calcium is soluble in water. I hope I answered your question, my dear.
Yes, thank you.
You're welcome. So let's clear this and move on. We are going to get closer to that again. So in hard water, I said, in hard water areas, an insoluble scum forms when soap is used. All right. Now, this problem has been overcome by the development of synthetic soapless detergents. In some textbooks, they are called soapless soap. Some textbooks should simply call them detergents, and some other ones will call them soapless detergents. Now, soapless is just to emphasize the fact that they are not precipitated by calcium and magnesium. Okay? They are not precipitated by calcium and magnesium. The structure of sodium 3-dodecyl benzene sulfate. Don't get bothered. Nobody's going to ask you to name name it, but at least you should know something like, if you see something like sodium stearate, you should know that that is soap. If you see something like sodium palmitate, for instance, you should know that that is soap too, because you know palmitic acid and you know stearic acid. But this one is sodium 3-dodecyl benzene sulfate. This is detergent. This is the head of the detergent. This is the head of the detergent. So the salt that this head will form with calcium is still soluble in water. That means when this one goes into water, that calcium is present. Okay? If this detergent dissolves in any water sample where calcium is present, it will not precipitate with calcium. It will not precipitate with magnesium. That means it is unperturbed, it is undisturbed by the hardness of water. This is the reason why we say the development of synthetic detergents has taken care of that issue of hard water wasting soap. I hope that is clear. Now, there are some textbooks that will show you that the detergent molecule has this structure, OSO3 minus Na. It is still correct. It is just different types of detergents, okay, for different reasons and different features, which is not exactly why we are studying detergent today. What we want to see today is that this is the head of the detergent, okay? This is the head of the detergent, and this head is not affected by calcium or magnesium ion, or rather it is not precipitated by calcium or magnesium ions. Okay, this is in contrast to that of soap. Remember, soap head is CO, is actually like this, O Na minus, sorry, plus and minus there, and this is minus. So this is soap. This one, this head, can be attacked by calcium to form an insoluble scum. But this head here cannot be attacked by calcium to form an insoluble scum. And that is why detergents are preferred for washing, especially in hard water area. I hope this is clear to everyone. Is everybody following?
Yes.
Okay. Any question?
No, sir.
Okay. Fami Roju, any question? Emmanuel, any question? I don't know what happened. It's like network. Today's network is Chimamanda. Chimamanda, any question? Chimamanda, I hope you understand all these explanations.
Yes, sir.
Okay, very good. Who else? Ruth. Ruth, any question?
Um, there are some detergents that, when used to wash clothes,
Yes.
usually foam more than others. Sometimes if you put it inside the water, they foam, and then after some time, it looks as if they stop
Before
foaming, while
this.
others stay longer than usual.
Okay.
Is there a particular reason or a particular ion that makes a foam last longer? The
Okay.
soapiness of the thing last longer.
Okay. Actually, what soap or detergent or whatever, all those surfactants, what they do is to reduce the surface tension of water, and that is why they form those bubbles. Okay, that is why they form those bubbles. So if the fabrics you are washing, there are many of them, and there are many grease stains, there are so many dirts, the color, your cuffs, you understand, the cuffs, your collar, and all that. If there are so many fabrics, you see that all the soap molecules are very busy burying their tails in grease all around your fabric. There will be no enough molecules to, what do we call it now, to be causing lather, because they are already active doing something else. You understand? They are not available for ladder. They've been buried into grease stains. That is why if you are washing very dirty clothes, if you're washing clothes that is very dirty, especially dirty with grease, you see that you may not find any ladder for a long while. In fact, finding ladder while washing means that it's either the cloth is not very dirty, or you are using plenty soap. That said, there are so many uh, chemicals that are added. They are called foam boosters. Foam boosters. Okay, all these foam boosters, they are also surfactants. Okay, so they are added to increase the lather strength, to increase the lather quality of the detergents. So some may have plenty, some will have less, some will have up to 2 or 3 different foam boosters, some will have just 1 or 2. You understand? So the quality of the detergent depends on how much surfactants are present, foam boosters to help in the foaming, all right, and all that. So that is actually dependent on the quality. It depends on the quality. And additives now, that's what I mean by quality. Depends on the additives. So I hope I answered your question now.
Yes.
Very good. Very good. Any other question, please? Okay, if there is no more question, we'll begin to look at what we will call the well, okay, let's tidy this up. The calcium and magnesium salt of these detergents are water soluble. So the problem of scum is solved. Very many of our washing powders and liquids contain this type of substances. The very common detergents we have now contain mainly detergents. So let's quickly look at manufacture of detergents as it differs from the manufacture of soap. Detergents are fairly cheap to make and are rapidly replacing soaps. The general process involves initially the reaction of a long straight chain alkene, such as dodecene, with benzene. Okay, so when you react dodecene with benzene, you get the benzyl dodecane. Okay, you get the benzyl dodecane. This compound is then reacted with concentrated tetraoxosulfate 6 acid to give a compound that is known as sulfonic acid. Now, this is called sulfonation. This is called sulfonation. Okay? These days, soapless detergents such as these are to be found in most washing powders and liquids. So you see that detergent is manufactured simply by sulfonation of hydrocarbons. Sulfonation of long-chain hydrocarbons. So I want to connect this to what we have learned before. Okay, some people probably haven't done it, but I'm still going to ask it all the same. Who can tell me where we can naturally obtain long-chain hydrocarbons? Long-chain hydrocarbons. Some of you told me that, no, you should have known. All of you would have done it. Everybody here is supposed to have done it. Yes?
So you said done it. I don't understand.
You've done it in hydrocarbons now.
What's the it?
Huh?
What's the it?
Okay, let me elaborate on the it. Okay. I said, who can tell me a natural source of long-chain hydrocarbons that we can now sulfonate to get detergent? Natural source. I hope you understand what I mean by it now. The hydrocarbon, the long-chain hydrocarbons. Nobody? No, now. You have done hydrocarbon. Have you done crude oil? You've all done crude oil here. You've all done crude oil as a natural source of hydrocarbons.
Yes,
Okay?
crude oil.
And when you separate, separate the fractions of crude oil using fractional distillation, you get different fractions. And as you go down, the fractions get longer. The chain of these fractions get longer. So your natural source of long chain hydrocarbons should be crude oil.
Yeah.
Yeah, that means we can use crude oil to make detergents. There's somewhere I'm getting to. You can use crude oil to make detergents. So detergent is an indirect petroleum product. Is somebody listening to me?
Yes.
Crude oil is raw material for manufacture of detergent. That means it's an indirect product for indirect product of crude oil. Exam bodies will ask this thing. They usually ask these questions and students do not really understand it. They could say, which of the following is not a petrochemical product or is not a petrochemical? Then when they put detergent, some people will be like, oh, dear, be detergent. What business does detergent have with petroleum? Of course, petroleum is the raw material. Okay, it's the raw source, it's the main raw material for the long chain hydrocarbon that is used to make detergents. But if you look at fats and oil, in fats and oil, our raw material is fat or fatty acid, isn't it? They still have the long chain hydrocarbons, but their head is different. Okay, the head of the molecule is different. So that one is for soup. I hope you all understand that. So the next thing we are going to look at is we'll look at the differences between soaps and detergents. Now, from what we have done so far, who can give me one or two differences between soaps and detergents? So,
Soap is derived from oils
very
or
good. Very good.
vegetable oil, animal fat,
Very good.
while detergent is derived from petrochemicals.
Very good. So soap is made from oils or from fats, okay? While detergent, you should write it down, while detergent is made from long chain hydrocarbons or from petroleum fractions. Let's make it simple that way. Let's say from petroleum fractions, so that you remember it. Petroleum fractions. Okay, that's very good. Ugoma has given us one powerful difference there. Okay, so next, who can give us another difference?
Soap, when added in hard water,
Beautiful,
forms scum when
beautiful,
attacked by calcium
beautiful,
ions.
beautiful. Soap forms scum with hard water. So forms scum. And for emphasis, because exam bodies like bringing that up, let's call the scum, let's say calcium stearate. Calcium stearate. Okay, forms calcium stearate, while detergents don't form scum. Detergents don't form scum. Okay, who can give us another one? Very good. We are making good progress. If you look at some things I said about them, you will know that you see that there are some differences that were silently mentioned. Okay, soaps are more expensive to manufacture. Soaps are more expensive. He's stretching his small body there. Soaps are more expensive to manufacture. Soaps are more expensive to manufacture. What about detergent? We say it's cheaper. Detergents are cheaper to manufacture. Okay. Any other one? Which one do you think could be more biodegradable? Which one do you think could be biodegradable? Pay attention to the sources. Which one do you think could be biodegradable? Is it soaps or detergent?
Soup.
Soup, very good, because it's from organic, natural, matter. So when you use it, The molecules will be broken down by bacteria. So soaps are generally biodegradable. Right? Let's write that down. Soaps are generally biodegradable. Okay. What about detergents? Though now the thing is that modern detergents are biodegradable. All right. Modern detergents are biodegradable, but detergents are mostly non-biodegradable. So let's write that first. Detergents are mostly non-biodegradable. Non-biodegradable. Then we'll add a clause there. Most modern detergents are biodegradable. So most modern detergents are biodegradable. So these are four very important differences between soaps and detergents. So once more, I'm going to ask if you have any question before we close for the day. Does anybody have any question from what we have done today? We've talked about soaps. We've talked about manufacture of soap, structure of soap, cleansing action of soap. And when we say cleansing action of soap, it's the same cleansing action that detergent will obtain. Are we together? It's the same process. Both soaps and detergent. The only difference is that detergents cannot be attacked by calcium, but soaps can be attacked by calcium to form scum, like we earlier mentioned, and we stated here again. All right. But their cleaning action is the same. All of them have hydrocarbon tail, which is insoluble. Then they have ionic head, which is soluble in water. All right. Okay. In the absence of any question, I'm going to ask my own questions. I'm going to ask my own question. I'll call your name. You will answer my question sharply. Don't run away. Don't run away. If you run away, I come to your house. Chimamanda. Chimamanda defines saponification.
Saponification is a process by which natural fats and oil are being heated with a strong of either plant or animals with a strong alkali.
Mm-hmm. To do what? Go on. What do they form? Hello, are you there?
Produce soap.
To produce soap. Very good. So what's the byproduct that is produced alongside the soap?
Yes, sir.
What's the byproduct? That's when soap
Glycerol.
is glycerol. Very good. Very good. Emmanuel. Very good. Chimamanda, please, everybody give her a thumbs up. Give Chimamanda a thumbs up. Quick, 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 quick. Thumbs up, thumbs up, thumbs up. Everybody, thumbs up. Very good. So, Emmanuel, your turn now. Ugoma, I did see your thumbs up. Oh. I'll come and collect that your thumb and paste it there. So, Emmanuel, unmute yourself, Emmanuel. Okay. Emmanuel, I want you to give me two advantages. Two advantages that detergent has over soap. Two advantages that detergent has over soap.
Detergent does not have any distraction.
Sorry, I didn't get that.
There's no distraction. There's no distraction from powder.
Network. Okay. Emmanuel, I want you to send it as a chat. That is your question. Go ahead and send it as a chat. Okay? Go ahead and send it as a chat. I'm going to ask Okafor Kenechukwu. It's your turn now. Okafor Kenechukwu, unmute yourself.
Yes, sir.
Okafor Kenechukwu, I want you to briefly describe how soup forms emulsion with oil and water. Basically, what I'm asking is describe the emulsifying action of soup.
Okay. So I'll use fabric.
Yeah, go on.
So when grease is on a fabric
Yeah,
and soap is and it's added into a soapy solution,
good.
the soap the soap covers the grease or forms around the grease.
Okay.
Then due to the action,
Hold on. Because you are about writing WAEC, there are some terms that I won't just allow to pass. Do you understand? I won't let them pass. I won't be light with them. You said the soap form on fabric.
no,
Is that
forms on
correct?
the grease
Sorry?
around the grease.
Okay. They surround the grease.
Yes, they
Okay.
surround the grease. That's what I said.
Oh, very good. Very good. Uh-huh.
So due to the action of soap, it tends to break the grease particles into smaller particles.
Okay. Is it the soap that does the action?
Mousse cells.
No,
Mousse
who
cells.
does the action? You said due to the action of soap.
Yes, the
Is
action
it
of soap.
is it the
Soap
soap that
molecules.
breaks it?
Soap breaks it. Yes,
Okay, you're sure that soap does the breaking?
Uh,
I think it is your agitation. It is your own scrubbing that does the breaking.
okay, yes. So,
Uh-huh.
I didn't
Uh-huh.
know. Okay. So the agitation
Mm-hmm.
breaks the grease into smaller molecules,
Very good.
in which I don't know where the mussels come in. Okay,
Okay.
the mussels. Okay, yes, the
Yeah, ha
mussels.
tabiri. Yeah, ha tabiri. They can't get musculus. Okay, the misers.
Nice.
Yeah, yeah. Okay, again, let's be very careful because our terms, there are small words that we mention. Don't be worried that I'm pausing you every now and then. It's because I want us to learn that there are some information, there are some words that you use that will make a mess of your answer. When you say it breaks the grease into tiny molecules, that's a problem. It does not break the grease into tiny molecules. It breaks the grease into tiny particles. Each of these tiny particles are now surrounded by soap molecules.
Okay.
Do you understand that part?
Yes.
Good. Each particle is now surrounded by soap molecules. Now, the surrounded particle is now what we call the micelle.
The myself.
And those can be easily washed away.
Yes,
Now,
sir.
when you are
Yes.
now talking about the emulsifying action, I want to support you there now. When you are talking about the emulsifying action, it is important to emphasize, that's where the emulsifying comes in, to emphasize that the micelles, those grease molecules or oil droplets, those grease particles or oil droplets cannot come back together. And this is
Okay.
because each droplet is surrounded by negatively charged soap heads. Negatively charged soap heads. Okay? And negative charges do what? Repel. That means each droplet will repel every droplet around it, keeping the grease or oil well dispersed or permanently dispersed in water. Okay?
Okay.
No, I know I gave you the toughest one, and you did well with it. Yeah, you did well with it. That's very good. So roots. Ruth, are you ready?
Yes, sir.
Okay. Ruth, I want to ask you the reason why we add salt to soup. Why do we add salt to soup? That's during the making, during the manufacture, salt is added. It is called salting out. Why do we add the salt? You have an idea?
Okay. Okay, salt. Mm,
What does the salt do? Pami Roger, I haven't seen your chart. Have you sent it? Okay. Ah, Pami Roger.
forms
Why?
as the
Okay, go on, Ruth.
it acts as the hydrophilic feature in the soap, which is water loving.
No.
And so when the soap is added into water, it then moves freely.
No. No. Actually, what it does is to separate the soap from the glycerol. It reduces the solubility of the soap in
Oh.
glycerol. Okay, you may want to put that down. Salting out or adding sodium chloride, adding concentrated sodium chloride reduces the solubility of soap in glycerol. Okay, good. So let's look at Famiroju's answers to as regards the advantage of detergents over soap. And he said that detergents, advantage of detergent, no distractions from calcium, and it's cheaper to manufacture. Very good. It's cheaper to manufacture. That concept of distraction is my illustration, which you trust me, you will not want to use in an exam. Okay, so instead of distraction, you say precipitation. Okay, precipitation. No precipitations from calcium ions. So detergents are not precipitated by calcium ions, just like soap. Okay, so you did well there too. You have all done well. Everybody give yourself a thumbs up. Everybody give yourself thumbs up. Thumbs up, thumbs up, thumbs up. Yes, 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 yes. Thumbs up. Yeah, we are good.